This video is about electric fields. So in physics, when we talk about fields, we're talking about an object's ability to exert force on another object without actually touching it. And so electric fields are a type of field we'll talk about in physics. We've already talked about gravitational fields, and we'll talk about magnetic fields later. So if you were to visualize an electric field, you actually visualize it as a bunch of lines. And there's rules for drawing these lines, and we'll talk about those right here. So if I wanted to draw electric field lines, which are the lines that emanate toward or away from a charged particle or surface, the first rule I would need to follow is that the lines always need to point positive to negative. So as you can see here, I have a positive charge around no other types of charges, and these arrows that indicate my electric field lines are pointing away from my positive charge. If I were to have a negative charge, my lines would point just the same way, evenly spaced as they were for my positive charge, but they would point towards the charge itself. So lines always point away from a positive charge and toward a negative charge. If I were to have, say, a positive and a negative charge next to each other, the lines would actually point toward the positive charge, or from the positive charge to the negative charge. So as you can see, all these lines are pointing from the positive charge to the negative charge, and the lines are still pointing toward the negative charge on the back, and the lines are pointing toward the positive charge in the front. And these lines are actually curving to meet the negative charge. And as you can see, that's going to be an important thing for our next rule, which is the lines can never cross. So as we talked about in the previous example, the positive charge and the negative charge, the lines went from positive to negative. The lines never cross in this diagram. And if I were to have either a positive and a positive or a negative and a negative, the lines would still never cross as I bring them toward each other. So the lines will actually need to bend to prevent themselves from meeting each other. So as these two positive charges are brought together, you can imagine that there would be an asymptote here, that these lines would prevent these lines from ever crossing. So these lines will go off forever into infinity and still never cross. For this reason, it generates a repulsive force when you bring two positive charges near each other, because the harder you're pushing these two positive charges, or even if they were two negative charges, closer together, these lines have to bend further and further and further, and that causes there to be more requirement for more force and more force and more force. The more you have to bend these lines, it takes force to bend these lines. The third rule for drawing electric field lines is that the lines are most dense where the field is the strongest. Okay? So if I have a charge of +1, maybe this is +1 coulomb, the lines will point away from the charge. And if I had a charge of +2 coulombs, that means that I have twice as much charge, so I have more field lines. So the density of the field lines around the +1 charge is less than the density of the field lines around the +2 charge. The fourth and last rule is that the lines always meet the surface of a conductor at 90 degrees. So if I were to draw 90 degrees here, all of these electric field lines emanating from this charged surface are meeting it at 90 degrees, even though the surface is curved. If I had two parallel plates, my charges would still point, or my electric field lines would still point positive to negative, but they would still meet the surface of both conductors at 90 degrees. All right? In the case of two parallel plates like this, all of the lines would go straight across, positive to negative, that are inside the conductor, but the ones on the edge will actually curve out like this. And this is an important thing to include on your diagrams, that you have these edge effects where the lines curve around the edge of a parallel plate capacitor. That's not a very good line, I'm sorry. I'm trying to avoid writing on my words. Okay, so that's how to draw electric field lines. So these electric field lines are an indication of the amount of strength that you're going to have at specific points in an electric field. And we define electric field strength in this class as the force per unit charge exerted by a small positive point charge at some point in the electric field. So we say it's a small positive point charge because we don't want the charge that we're using to test the field, or a test charge is another word to say this, positive test charge. We don't want the charge to affect the electric field by making its own electric field. So we say that it's really small, or we say that it's a test charge, and we always assume that it's positive, which is important. If we wanted to look at this mathematically, we would say we can start from our Coulomb's law. So 1 over 4 pi epsilon naught times a big charge times a little charge divided by the distance between them squared. And our definition of an electric field, so we represent electric field strength with an E. It says here that it's the force per charge. So if we combine these two definitions, the force exerted by an electric field and the definition of electric field strength, to get electric field strength, we would just divide Coulomb's law by charge. So if I divide both sides by charge to get the electric field strength, I'd get 4 pi epsilon naught, we'll assume that we're in free space, times the product of our charges divided by the distance squared, times 1 over the charge to divide our force by our charge. These two charges cancel out, and we see that the strength of the electric field is equal to 1 over 4 pi epsilon naught, our big charge that we're talking about generating the electric field charge, divided by the distance squared to the point that we're testing. So that, using our definition of electric field strength, is how we calculate electric field strength. So electric field strength is a vector. It has a direction, which means that we need to treat it like a vector. So if I have two charges, a positive charge and a negative charge here, both of these charges are generating an electric field, and we'll say that this point right here is the point that we want to test. So this is our test charge, or the point we're interested in. So if I wanted to know the electric field strength at this point right here, I would draw the electric field vector here. So this one's pointing positive to negative. And I would draw another electric field line for my negative charge, pointing positive to negative. This is a negative charge, so it'll point that way. I can add these vectors together, head to tail. So I have these two vectors added together, head to tail. And I see that my resultant vector is something like this, E pointing in this direction. So that would be my net electric field in this case. If we take a little more complex, so at this point where this test charge is, it's feeling this net electric field. If we wanted to make this a little more complicated, say I want to do this test charge in the middle here, and I have two equal positive charges on either side here and a much larger charge at the top, I can also do that. So if I I'm going to just draw a dotted line for these guys. This charge would be exerting an electric field in this direction on this small charge Q, on this test charge here. And this positive charge here would be exerting one in, this should be the same size, sorry, of the same amount in the leftward direction. This positive 2 charge is exerting an electric field at this point that's going to be larger than these two because it's a larger charge down. If I draw these vectors without the charges, so let's draw them all together, I see that these two vectors will have, let's say, look at this vector, it'll have a negative x component, and this one will have a positive x component, and they'll have y components that add together. And so I see that these two x components will cancel out. So I'm left with something like that. So this vector pointing down is much larger than this vector pointing up. So if I add those together again, I get something a little shorter because of this positive or vector pointing up, and I see that my net electric field at this point where this test charge is points straight down in space.